but you're someone who's looking for that guy, and you don't remember the spelling of their entire long, weird last name. So
Yeah.
you just type in the first 3 letters of their last name, and it would be nice to be able to find their phone number that way, right? You have the retrieval algorithm down now. This algorithm is actually exactly the binary search algorithm.
It's like the binary search tree completely solves the problem of like, well, how do we get our data sorted in the right place? Because the rules of the data structure sort it for you.
So we just learned about, so last time we learned about the binary search
Yes.
algorithm for arrays. And I want to think about like a generalized mechanism for storing and retrieving data, and which is what we've been circling around with, with linked list. So I want a generalized mechanism for storage and retrieval. And we talked about like linked lists versus arrays. And then last time we talked about, a specific algorithm you can do with sorted arrays and the binaries. Now the binary search can only work on sorted arrays. So
Right.
that's something that like it was a requirement. And it's a pretty big ask, right? Like, well, how do you get an array to be sorted? And we could talk about array sorting algorithms and the big old. Have you like read about array sorting algorithms before?
I have. It's been a long time. It's been many, many years, but I went
Right.
to a series of talks about it
Okay.
one time early on in my education process for computer science.
Do you remember the big O, the big O of the best sorting algorithm?
No, I don't remember that.
Okay. I'll just tell you. Yeah. Well, should I just tell you? Or let me continue the story. Oh, okay. I'll just say how sorting arrays is not fast.
Okay.
I'll just say that. Now it's when I say not fast, then what I usually mean is not better than big O of n.
Okay.
So sorting array, like fast is if I say something fast, I mean big O of 1 or big O of log n.
Okay.
That's what I mean when I say something is fast. So sorting arrays is not fast. And we may or may not dig into that this time.
Okay.
But so that's something. So which dramatically diminishes the value of the binary search algorithm,
Okay.
because
That makes sense.
you're telling me in order to use this really fast method, you have to prep it first with something that's not fast. And
Yeah.
and which makes the binary search much less attractive. There's a second problem though with and again, I'm thinking about a generalized mechanism for storage and retrieval, right? So
Okay.
I would like for both storing new data and retrieving data both to be fast, right?
Sure.
So and now we do have a thing that is fast for retrieving things. Like the binary search is very fast. So like a phone book is a good sort of reference point for
Okay.
like when you're thinking about what I mean by a generalized mechanism for like an application like a phone book. And usually when you, for simplicity's sake, let's say you type in a last name, and then I give you the phone number. That's the phone book app.
Okay.
And then it can do CRUD. So can do CRUD, which means you must be able to add in new phone numbers and along with the phone number, the person's last name.
Okay.
And you can delete entries. I guess you can update entries, like they changed their phone number, so you can change it, and you can retrieve it, right? And
Okay.
ideally, I want all of those operations to be fast, right?
Right.
How would you build that?
Okay. How would I build this? Well, I would start with putting something in place, a structure in place, whether it was a database or mocking a database, depending on
Well, you don't have a
the project.
database.
No database. Okay, so how's the data
So,
being stored?
yes, so the reason I'm not giving you a database is because um I want to motivate this computer science algorithms, because if you dig into what databases do, they're using data structures.
I see. I see.
Uh,
Okay.
so the stuff that database, there's a lot of things that databases do to make the CRUD fast in most cases, but in this case, we're trying to learn about how those structures work, so we have to do it ourselves.
That makes sense. So the names are going to be stored, or not the name phone values are going to be stored in an array, I would assume, since we're talking about array. Would that be the correct assumption?
Yeah, okay. Let's say, so like we have an array.
Mhm.
What do you put in each cell of the array?
Okay, I'm sort of thinking through it out loud here, but my first thought is maybe I'd have an object that has the name and the phone number
Yep.
in it,
Mm-hmm. So
in each slot or in each bin.
right. Yeah. Mm-hmm. So now, so the key thing is, just so that we don't have to go through exhaustively, but how to um, how to add an entry, and then how to retrieve an entry by last name, because that was our original requirement.
Okay.
What are our algorithms going to be?
Okay, so to add an entry, we're going to take the data that we're given, put it into an object, and then add it to the last available, to add it to the end of our array, is what I think. We would add it to the end of the array. So what is that? Push it to the end of the array.
Mm-hmm. We'll just say in most cases, it's big O of 1. Yeah, let's just say
Yeah,
it's big O
yeah,
of 1.
big O one. Yeah, I can agree with that. Yes.
Mm-hmm.
So that action is going to be big O of 1. Okay, so then to retrieve the entry by the last name is going to be a little bit more tricky because we have these objects with the name and phone number. They're going to be referenced by their index number. So we have to use something to find. We basically have to search through the array until we find the element that matches the name we're looking for.
Mm-hmm.
Um,
Which is how long?
yeah,
The big O.
but that's going to be big O of n. You know, it matters
Right.
how long. Yeah.
Yeah. So I would say that's not good enough because I want both operations to be fast, not just one.
Okay. So
So
it's back to the drawing board for number
yeah.
2.
Well, maybe I just say like. Actually, I should have written this down. So attempt one, add to the back, and then search whole array for match. So this is big O of n, and this is big O of 1.
Mm-hmm.
So this is not good enough. So attempt number 2. Can we do something with the fact that we know about the binary search algorithm and use that to make retrieval fast?
Yes, we can. So I was just sort of thinking that in step 1, maybe we don't just add to the back of the array. Maybe we do something different. Maybe we attempt to sort it as we're, creating.
Insert it in a way that
Alphabetically, maybe.
insert it alphabetically.
But,
By last name, right?
yeah, but I'm just trying to think through what that big O would be for
Yeah.
sort of like what the steps would be. I have to sort of think it out.
Yeah, I'll write down 2 first. So this would be a binary search.
Binary search. Yep.
By last name.
Yep.
And this we already know is big O of log n.
Yep. Which we're happy with.
Yes. So what is the big O of inserting an entry? And we're gonna assume that before the insertion, it was already sorted.
Okay. We've been maintaining this the whole time.
We've been maintaining this the whole time, and which would be perfectly fine if we started with an empty array, and then we just kept maintaining it, and every time we insert it, we kept it sorted, right?
Mm-hmm.
But how do you do this though?
Yeah, that's what I'm thinking through right now. I'm gonna just sort of talk it out. So the very first piece of data that comes through, no matter what that name is, it's going to be the first one. So you put it into slot 1.
Mm-hmm.
The second name comes through. You have to see if the letters are greater or less than. You have to do the comparison between what the existing record and the new record, and either push it to the end, it's greater than, or push it to the front, which would be, I guess, deleting the existing record, shifting it over 1, adding your new record to the front.
We have to do the shifting thing.
Yeah.
That's true. What if there's more than one thing in it?
Yep. So now you have 2. Your third one comes through, or let's just say you have 5 now. We've skipped a few steps. There's 5 names with values. You're adding a 6th. You have to compare the new 6th value with Okay, so you would start at one side or the other of your array. Let's just say you'd start at the beginning. You would say you'd compare it to the first value. Is it greater or less than? If it's greater, you're going to move on to the next value and say, okay, is it greater or less than this value until you find the slot where it needs to go, like in between.
So
Most likely it's going to be in between. Yeah.
So you're going to loop through each value in the array and compare.
Correct.
Until you find the slot where it fits in.
Correct. And then once you find that slot, you're going to have to do some shifting.
Right. May need to shift elements to the right over by 1.
Yes.
And then we're gonna insert new element. What do you think is the big O of this algorithm?
It's going to be in, I think.
Yeah, it's a big O of n.
Yeah.
So this whole well, I guess this is big O of 1, but that doesn't really matter. It's but this one is big O of n.
Yeah.
And this one is big O of n. And well, this is big O of 1. So at the end, the whole thing is big O of n. I would say step B. There's a faster way to do step B. Can you think of it?
Okay, so faster way to do step B, which is where we're looping through and comparing. Oh, could we could use binary search
Exactly.
in step B. All right, we could just yeah.
Yeah. So I'm gonna line through this guy.
Okay.
And yeah, exactly. We can use binary search. B prime is binary search to find the slot, which is going to be a big O of log n.
Okay.
Unfortunately, step C is still going to be big O of n. So from a theoretical perspective, we did not really improve, and even though we improved one of the steps, and that's a problem. So it's still not good enough. Basically, is the problem. Let's take a step back. Can you think of yet another solution to this problem, which might be might solve this for us, where both operations are fast?
Okay. We're trying to think of another solution to item 1, which is inserting alphabetically. Inserting alphabetically.
There was another data structure that we learned about before.
Okay.
That we can use here.
We talked about hashing hash tables.
Yeah, can we use a hash table here?
Let me think about that. Yes, I think we can. Yeah.
So how would that look like if we use a hash table for this?
I'm gonna have to refresh my memory on the hash table real quick. So with the hash table, we have basically everything is inside. Instead of being, okay, I might be wrong about this actually. Instead of with the hash table, our values aren't stored in an array. They're stored in the table, which is basically a big object. That's the way I think of it in my brain. Whether that's accurate or not, I don't know. So we have our key value pairs now. So we're going to have, I guess, the last name as our key,
Mm-hmm.
and then our value is going to be the phone number. And then okay,
Yeah.
but these need to be alphabetical. The wheels are turning in my brain that we still need to maintain
Well, I
them
didn't.
sorted.
Okay, so the alphabetical thing, I didn't explicitly give that requirement.
Okay.
Although it is relevant. So I guess my explicit requirement was you type in a last name and then I'll give you the phone number,
Okay.
right? If that was the only requirement, then you don't necessarily have to store it alphabetically.
Okay.
So let's just, but although there is an advantage of storing things alphabetically, which is that if you mistype the last name, then you'll get the neighbors of the name that you typed. And or like if you try to type in just a partial name, then you'll get all the things that match that partial name. If you stored it, or you could get the things that match the partial name if you store things alphabetically. So maybe that's like that's not a hard requirement, but that could be like a good enhancement. And
Okay.
actually that will make a difference. But for now, for now, let's say we don't require that. If
Okay.
we don't require that, can you do it with the hash table?
Yes. So with the hash table, we're just going to do a check to see if the name already exists. The name is our key. So see if our key exists.
Yeah.
I guess I'm probably kind of overkill here because that would be like, hey, if it already exists, override the number, and that would be like an update. But that we're not talking about that right now. So okay. So if the name doesn't exist, we add it. We add it to the hash table.
Yeah. Just if or there's if last name entry doesn't exist, just add the entry, the
Correct.
new entry, and then retrieval.
Retrieval is just the lookup.
Yeah,
It's just you have your key and you go grab your item. So the hash table solution makes a lot of sense in my mind. Like
yeah. Okay.
that we would
So
do that for this.
what's the big goal of 1 and 2?
Of 1 and 2, step one, it's going to be big O of 1.
Yeah.
And for 2, the same, because
Yeah.
it's just a search. Or a retrieval. It's a
Yep.
simple lookup. Yeah.
Yep.
So this is
Okay.
good. This
Yeah.
seems like a
That's the first contender, first
yeah.
real contender. So that's true. Hash table. That's why hash tables are really a staple of computer science, and
Yeah.
databases use it. All kinds of applications use it. I mean, if you're using JavaScript, then and you're using a JavaScript object, then you're using it. So yeah, this is a good contender, but because of the reason I mentioned before, it might not be the best for all cases. So so yeah, what if I want some kind of fuzzy search, right?
Mm-hmm.
Like I typed in, I have a really long name. Well, I don't. My last name is just 2 letters, but but for someone who has a really long last name, you might misspell it. So it would be nice to be able to type in, or you're not that person, because you probably remember the spelling of your last name, but you're someone who's looking for that guy and you don't remember the spelling of their entire long weird last name. So
Yeah.
you just type in the first three letters of their last name, and it would be nice to be able to find their phone number that way, right?
Yeah.
And with a hash table, that's not possible. You're just gonna get nothing if you misspell any part of the last name.
Right. It's an exact, it's like it's looking for the whole name as a piece. So we want to do some sort of, we want the ability to do some sort of search where we find any last name with the three letters CAR, in sequence. We want everything to come back that has CAR in sequence.
Right. So we want, so new requirement. So now that we have a winner, we're not satisfied. We're gonna change the yard marker. New requirement, we want partial matches. So like maybe they type in Jeff, and then it should be able to give you like Jefferson and stuff like that.
Yeah.
So now I guess the reason I want to bring this up is that we could satisfy this with attempt two, or not satisfy, but we could get the retrieval to be good with attempt two or solution two,
Yes.
because a binary search, we have a sorted array sorted by the last name, and we can really quickly find the right place in all of our names, and then you can just, once you find the spot, uh you can just like start there and then maybe go down until you don't have matches anymore. The problem though still is the insertion is slow.
Yeah. Yeah, that's the big problem. And I'm still
Yep.
not sure what the solution is. I'm still
Okay.
thinking. The wheels are still turning.
No. Okay. So I'll tell you the solution. The solution is a tree. So that's what we were building
Okay.
up to. So
Okay.
why do we want a tree? Well, so I'm gonna transform the sorted array into a sorted tree.
Okay.
And I'll show you what that looks like. So last time we had a sorted array. I won't do so many numbers this time. Maybe like 5. Okay, and our numbers have to be sorted. Okay, so what if, again, we said that the biggest problem with the array is that if we want to insert a number into the middle of this array, then we gotta shift the ones behind it over by 1. And
Right.
that's a big of an operation. It's inconvenient. What if we can dodge that problem entirely? And this is how we're going to do that. We're gonna say, no, maybe I should use a circle for trees. We're gonna have 5 tree nodes. instead of 5 cells. 1, 2, 3. Hold on. No, too many. Go back. This is not a full tree. That's okay. That's okay. We'll make it fuller later. Okay, so 12 goes here. 8 goes here. 4 goes here. 37 goes here. And 72 goes here. And now with binary trees, each node can have 2 children, but in some of these cases, when they don't, then they have a null value for that child, which can later be used. So like this one, in reality, it has just null values for both of its children.
Okay.
Then we represent null values this way. So although we don't have to be so verbose about it, so I won't draw the last layer. So I converted this to a binary tree. And now what this allows me to do is I can insert new elements. And the way this tree is sorted is based on this rule. The value of my left child must be less than mine, and the value of my right child must be more than mine.
Okay.
Those are the only 2 rules. So these are in order. So these are the rules in order for a binary tree to be a valid binary search tree. So this is called a binary search tree to be more correct. So we have a binary search tree. Okay, so now if I'm gonna insert an element, say 20, I can add that. I'm gonna use a different color. I can add 20 here.
Okay.
And that I can do in big O of log n, because how do I do that? First, first I find the place that I should add the new value, and that's done with the binary search algorithm. And the funny thing is, the binary search algorithm is embedded in this data structure, because it's just like, I want to look for 20 in this tree. Let's look starting from the root. That's the root. Yeah, so is 20 greater or less than 12? Oh, it's greater than 12. Based on these 2 rules, I know that 20 must be in the right of 12, right? So I go to the right side and I find 37. And then I say, hey, is 20 greater or less than 27? No, it's less than 20. Sorry, less than 37. is less than 37. So I go to the left of the left side of 37 to its left child. And then in this case, I find nothing. And if I find nothing and I want to insert something, I can stick it in there.
Okay.
Yeah. So what do you think about this scheme here?
I like it. I like it. It's very new to me. I haven't thought very much about it before, about it before. So now I'm wanting to sit down with a piece of paper and step through it like a whole bunch. Like my brain's going, okay, well, what if you wanted to add 21 next? Where would it go? Like all the things. Like I just want to see it in
Yeah.
action. I'll do that later.
Okay. Cool. Yeah. So maybe yeah. What if so? What if so? I guess we could try different things. Yeah. I mean, it's your session, so you can ask whatever questions you want. But I guess going back to the roots of how we analyze data structures, we look at like how do you create. We look at the CRUD. How do we do the CRUD? So for the binary search tree. So we already saw an example of we created a new 20 value inside this tree.
Mhm.
And I kind of hand waved over where to find the spot to put it. But that algorithm is more or less the same as the retrieval algorithm. So let's talk about the retrieval, right?
Okay.
Retrieve a value in the tree, retrieve. So given, and then all of these nodes could contain structures, right? That has multiple things in it,
Sure.
like a person's last name and a phone number. So you could also imagine in each bubble there's a last name and a phone number as well. But if you do that, um, then one of them needs to be specified as the key,
Okay.
because you can only sort, because the tree is inherently sorted, right?
Yes.
And we have to either sort by the last name or the phone number. But for our application, we're going to sort by the last name, right?
Makes sense. Yeah.
And if we're going to sort it alphabetically, that means, we'll probably put Adam, or yeah, add last name Adams here, and
Mhm.
put like Jefferson somewhere in the middle, etc.
Yeah.
Right? Okay.
Yes.
So,
Yes.
but then yeah, that's the key. But under the key, there could be other values like the phone number and even other pieces of information. So yeah, what is the retrieval algorithm? Maybe I'll just ask you. Can you write me, if I ask for any number, and it's same as the array index of method in the case of numbers anyway, well, actually it works for anything. So I want to like index of, oh, in this case there's no index
Yeah,
actually,
I was about
so
to ask about that. Yeah.
no, sorry, so that was wrong. So in this case we don't really have a concept of index, so this would more be like, mm, retrieve the thing if it exists. In if like assuming that it has additional information like phone number, etc., then you'll be able to get it. So this example is contrived in that we're
Sure.
only putting the numbers in there, so there's no additional value. But you could ask the tree, does this number exist in the tree or not?
Sure. Yeah, that's a good way to look at it in this
Yeah.
example.
Yeah. So does it, yeah, does a number exist How would you do this?
Okay, so we're going to ask, does 8 exist? So we're going to go to the
maybe I should just say find number.
find
And
number.
find a number, yeah. And then maybe even though we don't have any associated data with that number, you could still return the node. I don't know. Okay, yeah, just go with that. Find a number.
Okay, so I want to start with finding. I'm just going to sort of step through it mentally, one step at a time, and talk it out. I'm starting with a number that I know does exist. So we're saying, hey, do we have 8? Can we find 8 in this tree? So we're going to start at the root, and then we're going to read the number that's at the root, and we say, hey, it's 12.
Yeah,
and then we're going to ask ourselves,
12.
We're going to ask ourselves, is the target number less than or greater than 12? And since it's less than, we know based on our rules that it's going to be to the right. So we look down at the next node, and there it is. It's 8. That wasn't a very long example, but that's okay. And then we can return whatever we need to return.
Go left, I believe.
Oh, sorry. Did I get it backwards?
Yeah, go left.
Go left. Sorry.
Yeah.
I'm really bad with left and rights. I'm a left-handed person, and I always split them. Sorry about that. Okay, so now we're going to look for, oh, sorry. Well, I won't get ahead too far. We found 8. We returned it. So now we'll look for something that we know, because it's small, doesn't exist. We're going to look for 86. So again, we start at the root. We find our number. Our root is 12. We're going to go to the right. Wait. Left. No. Okay. No, hang on. I'm getting mixed up because I'm looking at what's written left and right, and then the screen is a mirror to me.
Well, you can say which number that is a child of 12.
Perfect. We're going to go into 37 because we know that 86 is larger than 12. So we're going to go down that side, the left side. And then we're going to say our next node is 37. Do our check, is our target greater than or less than 37? Well, it's greater. So we're going to go left again.
Go to 72.
Or am I saying it backwards? We're going to 72.
You're saying it backwards.
I'm still saying it backwards. Sorry. Yeah. And we're going to go to 72. And we're going to repeat the process. We're asking ourselves again, is my target greater than or less than 72? Well, actually, at this point, I don't know where in the process it would happen. When we get to 72, I think we would probably know this is the end. Like there's no more, that we see that the child nodes of 72 are null.
Oh, yeah. I mean, there's 2 ways of doing it. But if you have some time, I would suggest implementing this algorithm yourself. But essentially, you're going to need to check that null pointer, right?
Right.
That child value. Check to see if it's null. You could check it at the top level, or check it. You could say go right here. You could say go right to go to the right child of 72, basically. And then in the next step, you could end up with the node is null.
And then we would say, hey, our target is not in this tree. We got to a null terminus, like.
And then now we just return nothing. We return null for the whole function. So that's the like more succinct way to do it when you're actually writing out the algorithm, because you're not having to say, is the left child null, is the right child null? You're just testing at the top level, is the current node null. And
Okay.
but yeah, but it'll work either way. Yeah. So basically, yeah, you have the retrieval algorithm down now. Um, and um, and it this algorithm is actually exactly the binary search algorithm. I think it's pretty amazing. Um,
Yeah.
I actually didn't make this connection until years later. Like I learned, my professor in college taught me this stuff, and they never connected this to the binary search algorithm for arrays for me. But
Mm.
they are actually the exact same thing. And I think that's really cool. Um,
Yeah.
uh, yeah, you see how it, but it's like such in a such a different context though, isn't it? Like whereas in one you're like traversing this tree, but in another one you're like moving pointers in an
Yeah.
array. It just visually it seems very different, but they're so the same.
Interesting. Yeah, I'll have to think about that one some more. And not that I don't believe you, but just to like let it marinate in my brain. And yeah. Yeah, but
It,
it seems so much more intuitive here. Like
yeah,
I
but
feel like I was able to talk it out
yeah,
more
actually
easily.
just to hammer home my point, right? Like, okay, I'm gonna this recipe here. I'm gonna move it next to my array, and then I think this will pan out because the difference in the arrays doesn't really make a difference here because this 20 we never encounter 20.
Mhm.
So if we do a binary search on this array, um, first we're gonna look at the middle, right, which is
Yeah.
12.
Yep.
Yeah. So we're like, okay, is the number 86? 86 is greater than 12. We should go to the right, right?
Right.
Okay, there's two pointers. Yeah, so I'm not. Let's not skip that. But initially we're like, okay, we have two pointers, and then we went to the middle, and then we did the comparison, and we know it's in the right range. So I'm gonna move the left pointer to the middle now. And then in within the right range, I'm gonna make a new middle pointer, and that's gonna look at 37. Look, node 37.
Yeah.
We're looking at 37, and then 86 is still greater than 37, so we're gonna move to the right again, and then basically we're gonna replace the left pointer with the middle pointer, and then uh, we're gonna here in the tree we say we're looking at 72. In the binary
Mhm.
search we probably could have stopped already because there's nothing in between these two now,
Right.
but if we could have decided to let's just keep going, and if we do the division it's either gonna point to 37 or 72, one or the other, right? And let's say
Yes.
it was 30, let's say it was 72, then we would be looking at the node 72, and then we'll find that, oh, 86 is greater than 72. So it's somewhere over here, but that's beyond the bounds of the array, and therefore return null.
Yeah. Yeah. That's helpful to step it out that way. Like I said, not that I didn't believe you, but it helps to sort of make a solid connection there. That's really cool. It's like the binary search tree completely solves the problem of like, well, how do we get our data sorted in the right place? Because the rules of the data structure sort it for you so that you can always use a binary search.
Yeah, it's tailored for the binary search, which is why it's called the binary search tree.
Yeah.
Um, and out there, Okay, we're getting low on time, but
Yeah.
but there's a lot more to cover. So
Okay.
maybe we should
Next
just
week.
yeah, we could just continue next week. But I guess the thoughts I want to leave you. Well, obviously we should maybe cover. No, okay. Updating is pretty trivial once you know this stuff because updating is just you find the thing and then you change the value, right?
Yeah. Yes.
And then deleting is deleting is the most non-trivial thing. Um,
Mm-hmm.
Creating is even maybe can get a little complicated as well. Maybe, but is the real problem is what if you have a scenario where you're inserting numbers into an empty tree and you insert them in order. So let's say you have 5 numbers, like 1, 2, 3, 4, 5.
Okay.
And then you're gonna insert them into an empty tree and you do it in order. So first you insert 1 and then
Okay.
you put 1 in a circle and then you insert 2. And when you insert 2, what you're gonna do? Well, obviously you're gonna go to the right side of 1 and put it here.
Yep.
And then when you insert 3, well, you're gonna go to the right side of 1 and then you're gonna go to the right side of 2 again. So you're gonna put 3 over here. And then where is 4 going? Well, four is going here.
Yeah.
And then 5. Oh, sorry, I put 5 there. I jumped ahead. 4 is going there, and then 5 is going here. And you get a tree that looks like this. What's the problem here? It is still a valid tree. It's
Yeah.
still a valid binary search tree because it satisfies these 2 rules. The value to my left child must be less than mine, and value of my right child must be more than mine. So that still is satisfied for every node in the tree. But there's a practical problem now.
Is
Uh,
it, I'm not at all sure that this is right, but is it like now you have to search through more to get to your grade or not? I don't know. That doesn't seem right. I'm not sure what the problem is. Not sure. Still thinking about it.
no, that is right.
That's the problem. Yeah, like you have now, let's say you keep going like this and you get to 572, you have to search through all of those before
Yeah,
you get to your large number.
exactly. Yeah. I mean, what does this look like? This doesn't look like a tree.
It looks like an array or
It
a linked
looks.
list.
Yeah, exactly. It looks like a linked list because we're not utilizing the left side of any of these nodes. So
Yeah.
we don't get to we don't get to partition our elements into 2 halves each time.
Well,
Like
what if
with
we just start at the largest number and start with 5? Oh, no, that would be, well, no, we can't do them in sequential order. We have to mix up the order
yeah,
when we're building our tree.
exactly. Yes, that's a very key. Well, that's one of the strategies, which is you randomize it when you're inserting into a tree. You don't do it in order, but there are other strategies to and this concept is called the balance of a tree, like whether your tree is balanced or unbalanced, and this is clearly a very unbalanced tree. And Yeah, so we'll explore this next time. But this is one potential problem with dealing with trees.
Cool. I'm excited to explore it some more next time.